Hello, let's continue our Sudoku adventure with Counting Clones by Strosahl. So, we have normal 6x6 Sudoku rules, so in each row, each column, and each 2x3 box, we are placing the digits 1 to 6 exactly once each. We also have clones in the grid, so the cages designate our clone areas. So this is the A clone, and this is the B clone. They're just labeled. So whatever goes in the A clone, cages marked with the same letter contain exactly the same digits in the same relative positions with rotation, not reflection. So they rotate. So whatever goes here, say a 2 goes here, then we rotate around 180 and we put a 2 here. And if a 1 goes here, we rotate around 180 and the 1 goes there. All right. Same for the B's. So the 1 here, we rotate 180, the 1 goes there. All right. And then we also have counting circles. So a digit in a circle indicates how many circles contain that digit. So for example, if I have a 2 in any of the circles, then I need exactly 2 2s in all the circles. So maybe another 2 right there. And now I'm not allowed to put any other 2s in the circles, even if I wanted to, because there'd be exactly 2. So if a digit appears in a circle, it appears that many times. If it doesn't appear in the circle, then it doesn't appear in the circle, and that's fine. All right, and that's it. Those are the rules. There's a link in the description if you'd like to try the puzzle yourself, and I'm going to get started right now. I think I want to color the clones just so I can remember what's what. So I'm just going to make this green, purple, orange, and that means that this, let's see, 180 goes here. So green, purple, orange. Now, I could use 3 different colors for these, but I might confuse myself a little bit. Right, so of course, when you have counting circles, the first thing you want to do is count them. I'll explain why in a second. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 counting circles in the grid. Now, the sort of lemma that you can prove for counting circles is that the unique digits, the distinct digits that appear in the circles, sum to the total number of circles. So in this case, the distinct digits that appear sum to 8. Now, why is that? Well, because if, say, a 3 were to appear, say a 3 were to appear in a counting circle, well, then that uses up 3 of the counting circles in order to put 3s in them. I'm not worried about the red there. It uses up 3 of the counting circles. And so now there's only 5 left. So you can say that a 3 in the counting circles removes 3 of the counting circles, right? A 4 in a counting circle removes 4 of the counting circles. So it's almost like a subtraction from the total. So we can't put like a 6 and a 5 in these counting circles because we would need 6 circles with a 6 and 5 circles with a 5. That's 11 already. So yeah, the digits that go in these add to 8. Now, we don't know if it's 3 distinct digits. I was going to say 3 distinct digits adding to 8 require 1, but I don't know why I thought there needed to be 3 distinct digits. So we know there's at least 2 distinct digits. Let's see. You can see every row has a circle. Every column has a circle. Every box has a circle. So that doesn't restrict us. You can restrict 6 out of the circles, right? If there's like if one of the rows completely doesn't have one, right? But we could put 6 6s in here, technically. So the only thing I know is that there's at least 2 digits, but we knew that already because they have to sum to 8. So there's either 2 or 3 distinct digits in the circles, is what we can say. It is quite possible to be 2 and 6. 3 and 5, maybe. Okay. So I don't know what's going on with that yet. We probably need to do something with the clones then. I'm going to give this 3 distinct colors, but we need to remember that. I'm going to do it this way. Boop, boop, oops. Boop. We need to remember that some of these colors could be the same as some of these colors. I just need to designate how the clones work. So the red 180 goes here. So this is red, yellow, blue. All right. So is there anything we can say about these? I'm tempted to say these 2 circles are the same, but I mean, that's just that's just a guess. That's not necessarily true. We know there's a 2 over here. We know there's a 5 over here. Okay. So we know that purple or at least purple or orange is blue. Or sorry, we need a purple and an orange down here. So even if we put a purple or an orange down here, we'd still need the other one over here. But actually we can say this one's not purple. So actually one of these two is a purple. So either blue or yellow is also purple. And we get the same exact deduction over here. Yeah, one of these is purple, one of these is purple. Is that helpful? One of these two is yellow. You could easily be yellow, purple. Green is in one of these two. I don't know that I'm helping myself here. Should we think about, I mean, we only have 2, 3, and 5 place, so we're not going to have like a naked single or anything. Do I need to consider whether 2, 6, and 3, 5 are actually possible? So let's say I wanted to place 6 in the counting circles. I would need, this would be forced to be a 6. I'll write it out, but just to demonstrate what's going on. Because this row only has one circle, and every row will have to contribute a 6 to the circles. That means this row contributes a 6 here. This row contributes this 6 always, and this 6 always. Now this row would have to contribute this 6, and this row now could not contribute this 6. Okay. So the issue, oh yeah, so there's actually a pretty simple explanation here, which is this box here. The issue is that this row needs to get a 6 from this box, and this column would need to get a 6 from this box. That obviously doesn't work. So no 6s in the circles, meaning it's not 2 plus 6. What about 3 plus 5? That's a little bit harder to prove. We know the 3 wouldn't go in these two. We know the 5 wouldn't go in these two. And that's already enough to exclude it. Because this row can't contribute a 5, and this row can't contribute a 5. And so there'd only be 4 rows that could contribute a 5. So we're not 3, 5. We're not 2, 6. So we need 3 distinct digits without using a 5 or a 6 to add to 8. So we are 1, 3, 4 then. That's nice. Okay, I just need you to think about it more. So these aren't the 3, that's not the 3. So 1, 3, 4 go in the circles. Only one of them is a 1. I don't know which one. We are going to need 4 4s. That doesn't seem like a huge issue, does it? We need 3 3s. Okay, so we need 3 3s. And these are the cells that can be 3. So if you think about it, there's only going to be 1 3 in these two cells and only 1 3 in these two cells because of the column in the box I highlighted. So this has to be a 3. And now we know that the 3 doesn't repeat here, and we know that the red repeats here. So the 3 has to go here. And so now this can't be a 3. Remember, this box had to contribute 1, so this is our 3. This column still contributes a 3. All right, this is neat now that I've broken into it. Do I need all these colors? I don't know. So what's next? This 1 4 ends up down here. So this is a 1 4 pair. Why do I know that? Whatever this digit is, it goes exactly here, just because of the 6 by 6 roping. And so this can't be it also. These can't be the same. So if one of these is a 1, then we can't put a 1 anywhere else in the counting circle. So none of these are 1s, meaning we get the 4, the 4, the 3, the 4, and that gives us the 1 and the 4 there. So that's a 4. Very nice. That was neat. So what have we learned? Maybe green. Okay, I'm going to fill this triple. We need a 2, 5, 6. That's not 5. So this is also 2, 5, 6. And these are also, let's see, blue is 2, 6, and yellow is 2, 5, 6. Not a 2. So yellow can't be 2. What else have I learned? Maybe I can just place some 3s. Yeah, so this is a 3. Okay, 3s are done. What about 4s? Are 4s done? They are now. Okay, 3s and 4s got done. I need a 1 in this box. Is it red or is it here? I don't know. Let's fill this triple, 2, 5, 6. So this is only 2, 6. This is 2, 5, 6. That's purple, so this is 2, 5, 6. And that kind of agrees here. So that's, maybe I should get rid of these purples. That's confusing me now. I don't think that kind of coloring was going to be helpful. Is going to be helpful now. Do I want to think about, how about this column? We need 1, 5, 6. That's not a 5. So this is 1, 6 only. And then orange is 1, 5, 6. Okay. This column needs 1, 2, 6. The 1 in this column can only go here. And so now orange can't be 1. So now orange yellow is a 5, 6 pair. Oh, interesting. That means orange has to be blue. Wait, did I do this right? We know orange and yellow are different, so orange has to be blue. So orange is actually 6. I think this will work out. Orange is actually 6. That means red is 1. Yellow is 5. Blue is 6. This is 2 and 5, making this 2 and 5. Places this 5, this 6, this 2. Yeah, this worked out. This is a 2. This is a 1. We get the 2. We get the 1. We get the 6. And we're done. Nice. Correct solution. Neat. That last step there probably wasn't necessary, but I thought it was neat. Cool. In case it was unclear, the orange needed to end up here somewhere, and it wasn't the 1, and it couldn't be yellow because it shares a column with the yellow, so orange ends up there. I wonder if I could have... I don't think I could have made that deduction until I had placed all the counting circles, but after I placed the counting circles, I think I could have done that. All right, cool. Well, really neat puzzle, Strosahl. I enjoyed that. Let me know how you did. If you enjoyed it, why not leave a like, subscribe, and a kind comment below.